In Algebra 2, you talked about exponential functions. So we're going to review that a little bit here today. We're going to define what an exponential function is and use that for calculating compound interest. An exponential function is one that looks like this. F of x equals c times a to the x. Now, all of these are real numbers, and our constant c is going to be positive, and so is our a for all the ones that we're going to talk about. We're also going to make sure that a is not equal to 1. Now, why would we want that? Well, look at this function here. If a is equal to 1, well, what's 1 to the x? 1 to any power is just 1, so it doesn't really affect anything, and it would just be a constant and a horizontal line. So for a equal to 1, it's not really an exponential function, so we're going to avoid that situation. Now, all your exponential functions pass through the point 0, c. Whatever this c is out front, that tells you what your y-intercept is. And they all have a horizontal asymptote at y equals 0. Now, why is that? Well, if you have c and a are some numbers that are not 0, no matter what x is, no matter what power you raise it to, you're never going to get this to equal 0. So you have a horizontal asymptote at y equals 0. The other thing you need to remember is the difference between growth and decay. Exponential growth is when your a is bigger than 1, and decay is when a is between 0 and 1, when it's a fraction. Now remember, growth looks like this, and decay looks like, not like that. Decay looks like this. So you can tell this is growing as you go from left to right, and this is decaying as you go from left to right. So generally speaking, c is the initial amount. So if we have our function, this is generally the initial amount. And this is our rate of growth or decay. And that'll help you with word problems to find what kind of a function you're looking for. Now, most of these you're just going to graph on your calculator. Really, the only way to deal with it is to know you've got to cross at 0, 3 or 0, c, and figure out whether it's growth or decay, and then plot some points. So let's just look at a couple just to make sure that you remember this. Now this one, we've got our c is 3, so that means we're going to cross at 0, 3, and our a is 1/2, so that means it's decay. So when you graph this, you should see that you cross here at 0, 3, and it decays. Remember, the y equals 0 is your asymptote, so it's going to get closer and closer to that. What about this one? Well, 2 is our c, so we're going to cross at 0, 2, and our a is 3/2, so that's bigger than 1, so that means we're going to have growth. So you can put that in your calculator, and you'll see that you cross at 0, 2, and we're having growth like this. Now for these, you'll notice that the domain is all real numbers because x can be any value, and the range is y greater than 0 because we're all staying here. Now if your c is negative, then you would end up with y less than 0, but we're not going to deal with those cases. So for now, we just need to deal with y is greater than 0. Now, one thing we use this for is interest, and I'm pretty sure you looked at this last year too. So this is your principal, which means the initial amount of money that you put in to the bank. R is your interest rate in decimals. Make sure you put it in decimals, and it's your annual interest rate, so it's the one for the year. Your N is the number of compounding periods in a year, so the number of times they add the interest. So if it's compounded quarterly, then your N would be 4. If it's compounded semi-annually, your N would be 2, and so on. And then T is the number of years. So we can use this formula to figure out how much money we have if you put it in an account. Or actually, you can figure out loan payments and things like that too. This is for anything compound interest. Now, if it's compounding continuously, the equation's a little bit different, and we'll look at that differently. Now, notice that this is an exponential function. Our exponential function looks like this. So our principal amount, remember we said this constant C was our initial amount, and then this here, because it's compound interest, so it's how much you're adding on, so 1 plus, it's exponential growth, and it's our A number here when we have our 1 plus R over N. And then here's our exponent, NT in this case, because you'll have the T will be a variable, but the N will be a number that we can put in. So let's look at an example. So if we want to find the value on March 30th of 2012 of an account started on June 30th of 2002 with a deposit of $5,000 in a bank, paying 5% compounded monthly. So remember, our equation looks like this. The amount as a function of T is equal to the principal times 1 plus the interest rate over the number of times compounded raised to the power of the number of times compounded to T. So for this one, when it's 5%, that means our principal is $5,000. So that's how much we deposited. Now, with this formula, one thing you need to remember is basically what this is you put money in there and you just let it sit. You don't add anything to it. We're just looking at the interest. So we put money in there, $5,000, and we're just letting it sit. Our interest rate is 0.05% because that's our interest rate. It's compounded monthly, so that means it's compounded 12 times a year. And we want to know what happens between these two time periods. So how far is that? Well, it's not quite 10 years. It's 10 years and 9 months if you count it, because we've got July, August, September, October, November, December, January, February, March. So it's 10 years and 9 years and 9 years and 9 months, because it's almost 10 years. So it's 9.75 because 9 months is 3/4 of a year, which is 0.75 in decimals. Think about that. Make sure you've got that. So then you just need to plug it in. So the amount at 9.75 is equal to 5,000 times 1 plus 0.05 over 12 times 12, 9.75. All right, and you just plug it into your calculator, and you get $8,132.96. Now, what if you have this same situation, but instead of being 5% compounded monthly, what if we have 8% compounded quarterly? Why don't you try this one on your own? Pause the video and then see if you get it right. So hopefully you've already solved that one. So again, we have our principal is $5,000. Our interest rate is 0.08 this time. It's compounded quarterly, which is 4 times a year. And again, we're looking at the same time period, 9.75 years. So we just plug it in. And plug it into our calculator, and you should have gotten $10,823.72. Now remember, this is not saying A times 9.75. It's A as a function of time, and we're using an input value of 9.75. So this is just an input, not, it's that function notation. So make sure you've got that. We'll look at some more of this in class. Again, like I said, this is review, so we're going to treat it as review, and most of the exponential stuff and log stuff we'll do together as a review since you worked on it in Algebra 2. Write down any questions you have. Make sure you've read section 3.2.